Welcome to Part 14 of Applied Chemistry, where we will discuss solutions. In this section, we'll cover the properties of ideal and non-ideal solutions, Raoult's law, distillation, Henry's law, Nernst's distribution law, and the Arrhenius theory. A solution is a homogeneous mixture of two or more substances where the solute is uniformly dissolved in the solvent. Solutions are important in various fields, including chemistry, biology, and industry, as they form the basis for reactions, dissolutions, and various physical processes. Solutions can be classified into ideal and non-ideal solutions, depending on how they behave relative to their components. Ideal solutions strictly follow Raoult's law at all compositions and temperatures, with no volume or heat change upon mixing. The interactions between solute-solvent, solute-solute, and solvent-solvent molecules are equal, leading to ideal behavior. Examples of ideal solutions include mixtures like benzene and toluene or N-hexane and N-heptane. Non-ideal solutions, on the other hand, do not follow Raoult's law. They show positive or negative deviations based on the differing intermolecular forces. Positive deviations occur when the interactions between solute and solvent are weaker, like in ethanol and acetone, while negative deviations happen when the interactions are stronger, such as in a mixture of water and hydrochloric acid. Raoult's law is fundamental to understanding solutions, especially ideal ones. It states that the partial vapor pressure of each volatile component in a solution is proportional to its mole fraction and the vapor pressure of the pure component. Mathematically, this can be expressed as P1 equals X1 multiplied by P1 naught, where P1 is the partial vapor pressure of component 1 in the solution. X1 is the mole fraction of component 1. P1 naught is the vapor pressure of pure component 1. The total vapor pressure in a binary solution is the sum of the partial pressures of both components. In non-ideal solutions, deviations from Raoult's law occur due to unequal intermolecular interactions. Positive deviation means the vapor pressure is higher than predicted by Raoult's law due to weaker solute-solvent interactions. Negative deviation means the vapor pressure is lower, indicating stronger solute-solvent interactions. These deviations help explain why some solutions behave differently, with unexpected boiling and freezing points. This diagram represents how the Raoult's law work and what are the behaviors for ideal non-ideal solutions observed. Distillation is a key separation technique for solutions. Simple distillation is used when the boiling points of two components differ significantly, separating the more volatile component by vaporizing and condensing it. Fractional distillation is applied when the boiling points are closer together, and a fractionating column allows for repeated vaporization-condensation cycles for better separation. Azeotropes are special cases where a mixture behaves as a single component during distillation. For instance, the ethanol water azeotrope has a constant boiling point, making it impossible to separate by simple distillation. Henry's law explains the solubility of gases in liquids. It states that the concentration of a gas dissolved in a liquid is directly proportional to the partial pressure of that gas above the liquid. This relationship can be written as P equals KH multiplied by C, where P is the partial pressure of the gas, C is the concentration of the gas in the liquid. KH is the Henry's law constant, which varies for each gas-solvent pair. This law is particularly useful in explaining phenomena like carbonation in soft drinks, where CO2 is dissolved under pressure, and scuba diving, where nitrogen dissolves in the blood at higher pressures. Nernst's distribution law, or the partition law, governs the distribution of a solute between two immiscible solvents. The ratio of the solute concentration in each solvent remains constant at a given temperature. Mathematically, C1 divided by C2 equals Kd, where C1 and C2 are the concentrations of the solute in the two solvents. Kd is the distribution coefficient. This law is widely applied in extraction processes and pharmaceuticals, especially in understanding how drugs distribute between the bloodstream and cell membranes. The Arrhenius theory is foundational for understanding acids and bases. It states that acids dissociate in water to produce hydrogen ions. Bases dissociate in water to produce hydroxide ions. For example, HCl dissociates into H positive and Cl negative, making it an acid. NaOH dissociates into Na positive and OH negative, making it a base. This theory is crucial for explaining the behavior of electrolytes, substances that dissociate into ions and conduct electricity in solution. Strong electrolytes, such as NaCl and HCl, fully dissociate into ions in dilute solutions, leading to high electrical conductivity. However, in concentrated solutions, these electrolytes exhibit deviations from ideal behavior due to ion-ion interactions. The Debye-Huckel theory explains this by accounting for the electrostatic interactions between ions in concentrated solutions. Understanding strong electrolytes is key for studying conductivity and ionization in solutions. In summary, ideal solutions follow Raoult's law perfectly, while non-ideal solutions show positive or negative deviations due to differing intermolecular forces. Raoult's law explains the behavior of volatile components in solutions, and deviations help us understand non-ideal behavior. Henry's law governs the solubility of gases and liquids, and Nernst's distribution law explains the partitioning of solutes between immiscible solvents. The Arrhenius theory describes the dissociation of acids and bases, and strong electrolytes exhibit unique behavior due to ion interactions. We've reached the end of this video. Thank you for watching, and don't forget to like and subscribe for more tutorials on applied chemistry and other exciting topics.